Okay. These are your Chapter 4, Section 1 notes. These are just your TEKS. Your objectives are here. This is what we're going to go over today. All right, for this first part, we have the wave description of light. And keep in mind that throughout this section, we're going to talk about kind of two dueling theories, the wave description of light and the particle description of light, and also how they kind of come together as one description. But first of all, we're going to talk about the wave description of light. Electromagnetic radiation is a form of energy that exhibits wave-like behavior as it travels through space. All of these forms of electromagnetic radiation makes up the electromagnetic spectrum. And whether you remember it or not, you guys have history with this. You should have already seen this. So hopefully this is recognizable to you. So what we have going on here is this is the wavelength, okay? These are your values, and they're just in scientific notation. So this one is 1 times 10 to the negative 13, and this one would be 1 times 10 to the 5. All right, so you see these wavelengths down here are longer than these down here. Okay, so it would be accurate to say that gamma rays have shorter wavelengths than radio waves. All right, another thing to note on here is that also this, your frequency. So this is wavelength being shown here, but you need to also know that frequency is higher on this end. So gamma rays have a high frequency. Radio waves have a lower frequency. Okay, so as the wavelength is longer, the frequency is lower. All right, now here is the visible light. This is light you see, the colors of the rainbow. All right, something I know that you guys have done, hopefully you remember, is Roy G. Biv. Let me tell you how this is going to help you. All right, this acronym, red, orange, yellow, green, blue, indigo, violet. It will help you remember how the wavelength increases or decreases and the frequency increases and decreases with visible light. All right, so wavelength for visible light, it gets bigger or longer this way, okay? So I could label this wavelength increases this way, gets bigger. So red has the longest wavelength, and if you look right here, it does. See, it's longer than these. These get shorter, all right? And then frequency, though, increases this way in our visible light. I'll label this one frequency. All right, so violet has a higher frequency than red. Red would have a lower frequency, okay? So these are inversely proportional to each other. Okay, you absolutely will see that again. So make sure that you can remember that acronym and tell me how those wavelengths and frequencies get smaller or larger. All right. Wavelength is the distance between corresponding points, but it is also a variable that we're going to use in a formula. This is how I draw my wavelength symbol. Okay, so this symbol right here stands for wavelength. You absolutely need to know that because it's going to be a variable. Okay, this variable, V, stands for frequency. All right, so anytime you see the V, it means frequency. This means wavelength. Okay, here is your equation, C equals lambda V. Now, C is the speed of light in meters per second, and the speed of light is 3.00 times 10 to the 8 meters per second. Okay, so this is going to be a constant. Anytime you have C in this formula, you're going to plug in this number for C every time. Okay, these are going to be your unknowns. You're going to be given one, and you're going to have to solve for one. Okay, the units for wavelength, very important, is meters, okay? That's the units for wavelength. The most common unit for frequency that you're going to see, that's the V, remember, that's frequency, is hertz. Most common unit you're going to see. Keep your units in mind, okay? So let's go work a sample problem for this guy. All right. This is a problem you might see. Violet light has a wavelength of 4.10 times 10 to the negative 12 meters. What is its frequency? First of all, I know we must be using this formula because it's giving me the wavelength, which is this guy, and it's asking for the frequency, which is this guy. Hopefully you know that C is a constant, so I have C and I have wavelength, and then I can just solve for frequency. So go ahead and list out your variables. It's the best way to do it. So C is 3.00 times 10 to the 8. It always is. Okay, so that's our constant. Wavelength is this number right here they gave us in the problem. 4.10 times 10 to the negative 12 meters. And then frequency, we don't know it. That's the one we're going to solve for. Make sure when you're doing these, you check your units and make sure that it's in meters. They could give it to you in centimeters or even nanometers, which is fine because we have practiced on how to convert those. So you may have to convert in some of your problems, but in this case, it's good because it's in meters. All right, so let's just plug these in. So all I'm going to do is take my givens and plug them into this equation. All right, right over here with some room. So here's C. Okay, equals, and then for wavelength, I'm going to plug in my wavelength, 4.10 times 10 to the negative 12. And then I don't know what V is. All right, so I'm just going to rewrite V. So just do a little algebra here. These are being multiplied, so you do the opposite to solve for V. All right, so the opposite of multiplication is division. So I will divide by my given. They cross out, all right, so that I'm only left with V on that side, see? But if you do it to one side, you got to do it to the other. So I'm also going to divide this side by 4.10 times 10 to the negative 12. Okay, so when you put that in your calculator, and I absolutely suggest that you work these along with me, put them in your calculator, make sure that you can do these things and that you're getting what I'm getting. All right, so what you should get, and sig figs, we're going to use this, so three sig figs would be 7.32 times 10 to the 19. Our units for frequency, talked about it, hertz. So make sure you get the correct units as well. All right. Now, just real quick, I know you've probably seen this before, but remember, this is a visual representation of what wavelength is. It's the distance between crest to crest or trough to trough on a wave, okay? So, and also what you need to know is that this picture would have a low frequency. This one would have a high frequency, okay? Because basically at this fixed point, more of these waves could get by there with these short wavelengths than in these very long waves with this fixed point. So this one would have a higher frequency than this one. All right, so low frequency, high frequency, long wavelength, short wavelength. Okay, both of these are vocabulary words. You have them, you should be writing them down in your vocab, but just real quick though, the photoelectric effect is the emission of electrons when a metal, when light shines on a metal. So I'm going to have a visual for you in just a second on that. And then now we're getting into the particle description of light. And when you're talking about light behaving as a particle, then you need to have the definition for quantum, which is just the minimum amount of energy that can be gained or lost. Okay, so here's the light being shined on the metal. And what happens is when that light shines on this metal right here, it emits electrons and then powers this voltage system. So it gives it a voltage, okay? Or it gives it a, makes it have a current. All All right, hopefully this helps explain it.
When light strikes a metal surface, electrons may be ejected. This process is called the photoelectric effect. Each metal has a characteristic energy level. If the incoming light is below this level, no electrons will be ejected. For example, this red light is not sufficiently energetic to eject electrons from cesium metal. Yellow light is also not energetic enough to eject electrons. Green light is energetic enough to eject electrons and current flows.
All right, so that's the photoelectric effect. You may have to write a short description on your quiz, so make sure you can do that. All right, as we move into the particle description of light, you have one more formula that you have to be able to use, okay? And in this formula, let me get my pen back. You're going to have E is energy. The units for energy is joules, okay? So make sure that's your units for energy. H is going to be a constant. I'm not going to write it out because it's right here, okay? 6.626 times 10 to the negative 34. That is H, okay? So every time you use this formula, 6.626 times 10 to the negative 34 will go in for H, all right? And then, of course, V is frequency, and it is still hertz. So we had frequency in the last one, and the units are the same. They're in hertz. Okay, 6.626 times 10 to the negative 34. Let's work a sample problem for this one. And I'm just going to jot this down real quick so I don't forget it because it's on the other slide. So remember, H is our constant, okay? And I just wrote it down up there so I would have it. All right, our problem says a photon has a frequency of 2.68 times 10 to the 6 hertz. Calculate its energy. First of all, you need to know that we're using this equation. You know that because it's asking for energy, this is the only one that has energy in it. And it's giving you the frequency, which is here, okay? So that's how you would pick this equation to use. All right, so let's write our givens. We have E. We don't know. It says calculate the energy, right? So we don't know E. H is right here. Okay, I'll write it again. All right, and then V is given in our problem here. So 2.68 times 10 to the 6. All right, so after you write your givens down, all you have to do is plug them into your formula. So for E, I don't know it, so I'm just going to rewrite E. I know it's not very neat, apologize. For H, our constant, 6.626 times 10 to the negative 34. And then for V, 2.68 times 10 to the 6. All right, so again, I would put these in your calculator. Make sure that you can not only do them, but put them in your calculator correctly. So 6.626 EE negative 34 times 2.68 EE to the 6. Now, I didn't have to do any algebra on this one because E was already over here by itself. So you simply do what it says, which is just to multiply the two. All right, my sig figs would be 3. So I would want to round mine to 1.78. If you're looking at your calculator, it was 775. Round it to an 8. To the negative 27. Remember, our units, don't leave them off. They're important. Joules for energy. Make sure you put your units. Okay. Make sure you have the definition for photon. You don't have to write it down here. It should be in your vocabulary. But I mean, keep in mind a photon is that particle. So we are talking about the particle of description of light here. And a photon is that particle. It's basically a particle of electromagnetic radiation. Okay. It carries one quantum of energy.
In 1900, Max Planck theorized that a hot object does not emit electromagnetic energy continuously. Instead, Planck suggested that objects actually emit energy in small, specific amounts, or quanta. Energy, he said, was quantized. In other words, the energy being emitted has only certain values, almost as though the energy is a packet. Some wavelengths of light carry only a little energy at a time. Others carry more. But the energy is always quantized. It is always in terms of the packet. The smallest possible amount, one packet or quantum, is defined as the minimum quantity of energy that can be gained or lost by an atom. Quantization becomes important when light or another form of energy interacts with an atom. Sometimes the incoming energy is enough to make something happen, other times it is not. Think of rolling a ball out of a pit. The energy must be enough to get the ball out of the pit all at once, or the ball will simply roll back to the bottom. Even if the energy of multiple rolls would add up to enough energy, the ball will not have been able to get out of the pit because the energy of each hit in itself was not sufficient. With enough energy in a single hit, the ball escapes from the pit. Similarly, if the packet of energy is not large enough, the atom is unaffected despite the fact that the packets of energy keep coming. If the packet of energy is sufficiently large, however, the atom is affected. An electron, for instance, may become excited.
All right. So keep in mind, they're describing to you the particle description of light. Okay. Need these. So these are vocab words, and so I know that you usually don't write these down, but really make sure that you not only know what these are, but you can really explain it. So, if we have an atom here, and here's our nucleus, here's our protons and neutrons here in the middle, okay? And then we have our orbits around it. Okay, so real quick, if an atom is ground state, that just means that these electrons are in this lowest orbit right here, close to the nucleus. Whenever it gets sufficient amount of energy, it can become excited and move to an excited state, which is, say, this guy would just move out to one of these higher energy levels. So moving from a ground state out to an excited state. Just make sure you can explain the difference between those two and what that actually means. All right. You also will need to be able to describe the line emission spectrum. I know it's a vocab word, but this goes into it with more detail. Really understand that they pass an electric current through a vacuum tube. That just means in a vacuum, there's no air. Okay, so nothing affecting it. And in this tube, all it had in it was hydrogen gas. Nothing else, okay? When they did that, there was a pink glow. So they took this pink glow and they passed it through a prism. You guys know what a prism is, okay? When they did that, it separated it into the 4 colors of the visible spectrum, and that was called our line emission spectrum. All right, so here's our tube with hydrogen gas in it in a vacuum. All right, they passed a current through it, and it was pink. They shined it through a prism and it separated into the line emission spectrum. Again, be able to explain that. Okay, so Niels Bohr used that to explain orbits and how electrons can only travel in these allowed paths. Okay, and that this is super important. So, like this right here, okay, make sure you know that the energy of an electron is higher when it is further away from the nucleus. All right, got to know that. I need. Okay. Okay, I want to show you this, and that thing wasn't switching back over. So just real quick. All right. So this is going to explain the line emission spectrum again. Try to get a grasp for this.
In the late 19th century, scientists observed that a characteristic lavender light was produced when a high voltage electric current was passed through hydrogen gas. When the lavender light was sent through a narrow slit, then through a prism, it separated into distinct lines of different colors. In 1913, the Danish physicist Niels Bohr proposed a model of the hydrogen atom that explained atomic spectra. The Bohr model introduced the idea of quantized energy states for electrons in atoms. In the Bohr model, the electron moves in circular orbits about the nucleus. According to the model, the electron can circle the nucleus only in allowed paths or orbits. When the electron is in one of these orbits, the atom has a definite, fixed energy. While in an orbit, the electron can move to a higher energy orbit by gaining an amount of energy equal to the difference in energy between the orbits. When a hydrogen atom is in an excited state, its electron is in a higher energy orbit. When the atom falls back from the excited state, the electron drops down to a lower energy orbit, and a photon is emitted. The emitted photon has an energy equal to the energy difference between the higher energy orbit and the lower energy orbit.
All right. These are not vocabulary words, and you need them. So write down the definition of emission, basically what it was explaining in that simulation. When an electron falls to a lower energy level, that is called emission. Okay. You also need absorption. So when it moves from lower to a higher energy level, it's called absorption. So energy must be added for this to happen, and energy is emitted or lost when this happens. So write these down. They're not vocab words, and you do need them in your notes. Okay, so here, just real quick, this is the last thing in this. Here was the Thomson model. Okay, remember he thought that the protons and electrons were just scattered equally throughout. Here was the Rutherford model. He got the nucleus correct, but he was not really successful in telling where all these electrons were. And then the Bohr model brought it all together and actually said that not only is there this dense nucleus here, but these electrons are only moving in certain allowed orbits. So be able to kind of, describe this evolution of the atomic model and how it started here, kind of went to here, and then we ended up here.